is a sub 10 plus a sub 11 plus a sub 12 forever. What can you tell me about this one? What do you feel? It's also convergent. Now, will it be converging to the same number? No, but it should converge to a number, right? What the difference between this one and this one is only 9 numbers, right? This one had 9 more numbers than this one did, but they were finite numbers. So if I take those numbers away, then I should still have a convergent series. So that's what this is saying. Is that if you start with a convergent series and you take out a few numbers, or even if you add a few numbers, as long as it's a finite number of numbers that you're adding or subtracting, you should still maintain the convergence. It also works for divergence. What if I told you this diverged? Do you think taking out 9 things is going to change it? No. If this diverges and I add 9 more numbers, is it going to change it? No. So if you're given a convergent series, adding or subtracting a finite number of terms does not change the convergence. If you start with a divergent series, adding or subtracting a finite number of terms does not change the divergence. It has to be a finite number of terms. Clear or no? Y'all look tired. Turkey is this week. Then you're tired after, right? All right. We are now going to do the integral test. All right, so we are now, let's see, we have the nth term test, right? We have the nth term test, pregnancy test. We have the geometric series, which is kind of like a test. We test to see if it's geometric. We have harmonic, right? Those are our 3 different types of things we have in terms of test. This is now the 4th test that we're going to look at, the integral test. And I apologize, hopefully y'all can see this here. We're going to look at the test visually first. Remember that integral? Integral, not a series. Remember that integral? It's called an improper integral. Goes, in this case, from 1 to infinity. What that represented was the area underneath some curve, right? So if we had some graph, and we were to graph it from 1 to infinity, this is too big, there we go. We would be talking about the area underneath that. And we concluded a few sections ago that sometimes that area is finite and sometimes it's infinite. Sometimes it converged, sometimes it diverged. Remember with the improper integrals, it just depended? Okay, so going into this, we have to be comfortable with the idea that these improper integrals either converge or diverged. It just depends on the actual function that we have inside. Oh, I need a drink, hold on. All right. All right, so now we're going to look right now at a visual idea of a convergent integral. So if we have this integral, I should say convergent improper integral, if I were to find the area underneath this, right, that purplish area, I'm telling you right now that it's finite, okay, that converges. I'm telling you that, all right? So let's say that that is a finite area. And the example we're looking at right now is the function f of x equals 1 over x squared. We did that in class, actually. This is a number, right? That area is a number. All right? What I'm going to do now is I'm going to look at the sequence. A sub n is 1 over n squared. 1 over x squared, 1 over n squared. This integral is adding up this total area, isn't it? It's adding up this total area. This sequence is the same as this function. I would like to know the series of that. And I want to know whether or not this converges or not. Well, this converges, doesn't it? This converges. So the question is, does that? What does your instinct tell you? Not necessarily? Okay. I mean, it would be too nice if it was, right? It would almost be too nice if for us to figure out if that converged, all we have to do is figure out if this converges. That seems almost too good to be true, right? But I'm going to show that it actually is. Whatever this does, that does. But the way to show it is by doing this. Let's write out the first few terms here. This is 1 plus a fourth plus a what? 9, right? Plus, I'm plugging in 1, then 2, then 3, then 4, 1/16th, right? 1/25th, right? So watch what I do to this picture right here. I'm going to go to this picture and I'm going to draw a rectangle. Okay, here's the first rectangle I'm going to draw off this picture. This is 1, right? What happens when I plug 1 into this? I get 1, right? It's not drawn to scale, but when I plug 1 into this, I get 1, right? Do you all agree that if I draw this rectangle, the area of this rectangle right here, how wide is it? 1. How tall is it? 1. What's the area of that rectangle? 1, right? See that rectangle? That area is 1. The next rectangle I'm going to draw is that one right there. So what I'm going to do is I'm going to go to 2. When I plug in 2, what do I get when I plug 2 into this? 1/4, and I come over like this and draw a rectangle. How wide is it? 1. How tall is it? 1/4. What's 1 times a fourth? 1/4. Isn't that this number? Right? What I'm doing is those blue rectangles, the areas of those blue rectangles represent these numbers, right? The next one is going to be what? 3. I go up. How tall is it? 1/9, right? 1/9. So the area of that is 1 wide times a 9th high. 1 times a 9th is a 9th. That's this number. Y'all see it? I can continue that for all of them. So let me draw some more in here. There we go. So you tell me. Any questions on the picture here? Y'all tell me. If I'm telling you that this integral converges, that this goes to a number, that's the area of the purplish, right? I'm telling you the area of the purplish stuff is finite. What can you tell me about the area of all the rectangles?
They're also finite?
It's also finite because everything, look, this purple right here on this little strip, the purple all the way down, right, is bigger than this rectangle. So that area is less than this, right? This area is less than all that. This area is less than that. This area is less than that. So the area of all the rectangles should be less than the area of the purple, right? With the exception of one rectangle. There's one rectangle out here, this one. That's not part of this graph, is it? But isn't this just one number? It's just one number. And one number does not change the convergence or divergence of something. That's what we just said. If I had 10 extra numbers, it wouldn't matter. So if you just take out that first rectangle, all the other rectangles added up should be less than the area underneath that curve. And if I know that the area is finite, then I know that this must be finite. Now, do they add up to be the same thing? No. They don't add up to be the same thing. But I know at least this must converge. Why? Because that converges. If the integral converges, then so does the series. Now this will all be, we'll draw a final conclusion. I'm just trying to geometrically explain what's happening here. Let's try this the other way around. What if I tell you to start that the original area underneath here, what if I tell you that that area is infinite? What if I tell you that this area is infinite? In other words, this diverges. Let me look at what graph are we looking at? We're looking at 1 over x here, right? Looking at 1 over x. Okay, that graph looks very similar. At 1, you're at 1, and it drops down. We showed in class We showed in class that this diverges, it becomes infinite. So what if I start with that and I tell you that? And now we compare it to this. Now you already know what this does, don't you? What does this do? It diverges because why? It's harmonic, but let's act like we don't know that, okay? This would be 1 plus a half plus a third plus a fourth. So I know that this area is infinite, and now what I'm going to do is I'm going to start drawing rectangles in here. But I'm going to do it a little bit different. I'm going to draw my first rectangle like this. I'm not going to go up and to the left. I'm going to go up and to the right. And that goes to 2. The width of this is 1, and the height is what? 1. 1 times 1? 1. That's the first number. Then from 2, I'm going to go straight up and over and down. How wide is it? 1. How tall is it? Well, we have to plug 2 into this, right? 2 into there, we get a half, right? So 1 times a half is a half. Plus the next one, this was 3, go up, over, down. It's 1 wide, and how tall? 1/3. And that gives us this one, right? Do you see the difference the way I drew those and the way I drew the ones before? I went to the right instead of to the left. So if I continue to do that, I would get all those, right? And so these rectangles are above the curve, aren't they? They're above the graph a little bit. So if I add up all the areas of the rectangles, it should be more than the area underneath the graph. But the area under the graph is what? Infinite. So is this. This must be infinite as well because these areas are more. Yes?
Why are you drawing your rectangles going to the right?
Great question. I was wondering if anyone was going to ask that. Why did I draw them to the right? I did it to the right to make it work. Let me show you what happens if I go to the left. Okay, this is a very good question. If I go to the left, again, we're starting out by knowing that that's infinite, right? So what if I use the same convention I just did on the previous one? If I went up and over like this, right? Okay, how wide is it? 1. How tall is it? 1. That would be 1. I'm put a 1 in there. Yes? And that would be my first number. Now we go to 2. 2 and up and over, right? Now what's the area of that? A half? So we got this one, we got this one, and the next one would be this, and that would be a third. Do you see it's the same thing? But wait a minute, can you draw a conclusion? So what can you tell me about the area of the rectangles here? Is it less than or more than the area of the black? It's less, right? So that area under there is less than what? Okay, so does that mean it converges? No, if I tell you that something is less than infinity, does that mean it goes to a number? No, because you could say that less than infinity could still be infinity. Does that make sense?
Yeah.
What I'm doing is I'm drawing my rectangles in a way that I'm saying that the sum of these rectangles must be bigger than this. And the only way to be bigger than infinity is to be infinity. If I tell you that that sum is less than infinity, that means it still could be infinite or convergent. I still don't know. In the previous example, right, this was finite. The area of the curve, the area under the curve was finite, right, a number, and we showed our sum was less than that. And the only way to be less than a finite number is to be finite. If I showed that it was greater than a finite number, then that doesn't mean that it's infinite, and it doesn't mean that it's finite. You don't know. Does that help?
Yeah.
Okay. All right. So how about just what's the end story, right? What's the final conclusion of everything? The conclusion. The conclusion is that if you're ever trying to figure out what a series does, right? If you're ever trying to find out what a series does, what we do is we convert that function, and we convert the sequence to a function. And then we check to see if that integral converges or diverges. Whatever the integral does, that's what the series does. All right? Whatever the integral does, that's what the series does. But there are some catches to this. There are some conditions. And the conditions are written down on your formula sheet. The only way, you can only do this test if your function is, what does it say on your sheet? There's conditions for this test, for the integral test. Your function f must be continuous. Must be continuous. What else? Must be positive. What does positive mean? So conditions for integral test. For integral test. So your function must be continuous. You must be able to draw it without picking up your pencil. First condition. Second condition, it must be positive. Positive just means it's greater than 0. That means your function never dips down below the x-axis. And then what else? Must be decreasing. Which means that as you move from left to right, your function must be going down. If you have these three conditions, then you can do the test. I say we do an example. I think it's time. Oh, integrable. Yeah, so we have to be able to find the antiderivative. Because remember, we're going to do an integral. Like if you can't do the integral, you can't do it, right? All right, so this is in our notes. It says integral test, how to use it. So I'm going to go through this and just highlight this. So I'm going to give you a series, right? I'm going to give you a series. You're going to look at it, you're going to go, shit, I don't know what to do with this, right? What you're going to do is you're going to convert that, you're going to convert the sequence, right? The formula, a sub n, you're going to convert it to a function of f. Then you're going to have to show me that that f is continuous. You have to show me the f is positive. You have to show me that the f is decreasing. So you have to show me that these three things, these three conditions are met. And then after that, you're going to evaluate the improper integral from 1 to infinity. And then whatever that does, that's what your series does. So let's do these. I always wished that I could do a cartwheel. I can't do a cartwheel. I don't think I've ever been able to do a cartwheel. No, I'm not going to hurt myself. I'm not going to do it. I haven't done it this, on last day. That would be my last day probably when I try it. So when I put my daughter in gymnastics when she was younger, she did her first cartwheel. I was just like, thank you. It was like, that was my cartwheel she did, you know? Anyways, why am I talking about cartwheels? If I could do a couple of cartwheels right now, I would, just to kind of wake y'all up, to get y'all like, what the hell's going on in here? Okay? Because look, we got to get through this. Come on. This is got a lot to do here in chapter 8. So there we go. Does this converge or diverge? Let's just talk about what we know, what we don't know, right? First test we ever do is what? Nth term. I'm going to do it fast. This is the pregnancy test. Nth term. What am I doing? Limit. N goes to infinity of 1 over, yeah, this sequence right there, right? I'm doing that. And what am I getting? Fixed over infinity, right? That goes to 0. That tells me nothing, right? This test fails. Okay, then I look. Is it a geometric series? Well, do you see n in an exponent? Yeah, it's not geometric. Okay, is it harmonic? What's harmonic? Constant over linear. Is that linear? No, it's under a root. It's not linear. Okay, so I have nothing. I have nothing right now in my test, in my analysis of series. I have nothing that I can do right now. But now I have this new thing called the integral test, right? And I'm going to see if I can maybe use this. So what I'm going to do first is I'm going to convert the sequence to a function. All right? Oh, I should let you know what I'm doing. Integral test. All right. Now, I'm not just going to start cranking the integral out. I've got to check the conditions. First, is this function continuous? Is f continuous? Now, I only need it to be continuous on this interval 1 to infinity. Why? Well, I'm only going to integrate it from 1 to infinity, right? So I only need it to be defined there. Because there is a problem with that function at -1. Do you all agree? Yeah. But I don't need to worry about that because I'm only going from 1 to infinity. So this is good, right? Is it continuous? Yes, right? All right, next thing. Is f positive, greater than 0, on that interval 1 to infinity? So am I always going to get positive numbers out? Yes, because I'm plugging in numbers 1 to infinity, right? These are always going to be positive numbers. Square root of a positive number is positive. 1 divided by a positive number is positive. This is always positive, just by inspection, right? Now, you have to write this down, okay? You can't just, like when you take a test and you're doing the integral test, you can't just skip this step. This is important. You lose points if you don't at least verify these things, especially the next one. Because what do you have to show now? F is decreasing. Okay. How do we show a function is decreasing? Cal 1. Take the what? Limit. If we're trying, decreasing means the function's doing this, right? So what we want to look at is the first derivative. Remember, if the first derivative is positive, your graph goes up, right? If your first derivative is negative, it goes down. So what I'm going to do right now is I'm going to take the derivative of this and try and convince you that it's always negative. That's what I'm trying to do. So I want to show that the derivative of this is always negative. Are you ready for the derivative? Okay, what's the derivative of this function? Well, let's do this. Let's rewrite the function first. I'm going to rewrite it as x plus 1 to the negative half. You all right with that? That's just the original function rewritten. I rewrote the square root as x to the half power, and I brought it up. Now I take my derivative. Negative 1/2 comes out. I'm using chain rule. X plus 1 to the negative 3/2. And then times the derivative of what's inside, which is 1. I don't really need that. I'm just trying to remind you we're doing chain rule here. But all right? Now I'm going to rewrite this as negative 1 over 2 square root of x plus 1 cubed. So all I did there, put the negative 1 on top. I left the 2 on the bottom. I took all of that to the bottom and rewrote it as a radical. Right? 3/2 power means you cube it, take the square root. All right. Chris? Chris? You all right? That's all right. I don't want you to say you didn't know. Here it is. So is this always positive, negative? Can you tell?
Yeah.
How can you tell?
Because you're only using numbers greater than 0, so the bottom will never be negative.
Yeah, so the numbers in here are always 1 or bigger, right? So that's always a positive number. What's a positive number cubed? Positive. What's the square root of a positive number? Positive. What's 2 times a positive number? Positive. Negative over positive? Negative. This is always negative. This is always negative. Okay, so have we met all the conditions? Yes. We have a continuous function. We have a positive function. We have a decreasing function. The integral test applies. Now, sometimes showing this is hard, okay? Showing it's decreasing by taking derivative. So I want to show you your second option as to how to show something decreases. And that is, instead of looking at the function and showing that the derivative is negative, we're going to go back to the sequence and show the sequence decreases. We're going to show this decreases. All right? So we're done here, but I'm going to show you a second option. And this is in your notes too. It says it in the note right here. for the steps, right, there are two options. There are two options in showing that something is decreasing. You can either show that the derivative is negative, or you can show that we have a decreasing sequence. So I'm going to do that. So your other option is to show this. Show that f of a is bigger than f of b when a is bigger than b. Sorry, hold on. That's not right. This should be backwards. Look, here's what I'm trying to show you. If A is here and B is here, that when I plug this in, I get f of A, right? That's this point right here. And f of B needs to be smaller, right? So this number here needs to be bigger than this when that number's smaller than that. That's a typo on my notes, so I apologize. Okay, so how am I going to do this? What I'm going to do is I'm going to go back, recall how to show a sequence decreases. And for this to happen, I want to show this. I want to show that a sub n is bigger than a sub n plus 1. So if you go back to your notes, I was talking about decreasing sequences. In order to show a sequence decreases, I must show that the nth one is bigger than the next one. When you plug n into the sequence, like let's say n was 4, that the fourth number in the sequence is bigger than the fifth. And then you would say the fifth would be bigger than the sixth, and the sixth is bigger than the seventh. This is a generic statement, so each one of them is getting smaller, which means it decreases. So that's what it means to show a sequence is decreasing. I would like for us to go back and look at this sequence right here and show it decreases. So what is a sub n for us? 1 over square root of n plus 1. And the question is that bigger than what happens when I plug n plus 1 into the sequence? If I replace that n with n plus 1, I get what? 1 over square root of n plus 2, because it's n plus 1 plus 1. So is that true? You have to convince me or convince yourself that that's true. Is it? Yes or no? What time is it? Oh, we only have 6 minutes. It's true. Let me do this. I'm going to cross multiply. Are you satisfied with that? I'm doing a cross multiply. I don't have to worry about flipping the inequality because I know this is a positive number and a positive number, so I don't have to flip. So is that true? I think most of us can look at that and agree that that's true. What's underneath this root is bigger than what's underneath that root, right? So the square root of that should be bigger than the square root of that. So I'm good. So I have a decreasing sequence. If I have a decreasing sequence, then that means my function decreases as well. Because all my function is the sequence rewritten in functional notation. So when you're doing these problems, you can either show the derivative is negative or you can show this, but you have to show it. I'll have to do another example next class. But now we need to actually get to the test. Okay? Now for the test. All the conditions are met. Now I need to do the integral from 1 to infinity of 1 over the square root of x plus 1 dx. Whatever that improper integral does is what the series does. So how would you integrate this? Yeah, there's different ways to approach this. Do you need anything complicated? Like, do you need integration by parts or trig sub or anything like that? No, this is just a basic u sub. This is just a basic u sub. Okay, so the basic u sub here, I'm not going to show the work here. Not going to show the work. It should be 2 square root of x plus 1. That's the antiderivative. I'm not showing the work to get that antiderivative. I'm just doing it. And then we're going to evaluate this from 1 to infinity. Now, the way we did this back in improper integrals, we did a limit, didn't we? We converted to a limit. So I'm going to go ahead and do that now. I'm going to do limit t goes to infinity of 2 root x plus 1, 1 to t. And that's limit t goes to infinity. And now I'm going to plug in my two values. My t goes in first, 2 root t plus 1. Then I plug in 1, 2 times 1 plus 1. What happens? Yeah, you get infinity here, don't you? This becomes infinite. And that means this integral diverges. And whatever the integral does, the series does. Therefore, I need to draw a conclusion. Therefore, the original series diverges. All right, we have another example. We don't have time for it, but look at it real quick. Look at the actual sequence. N over e to the n. If we did the pregnancy test first, we take the limit of this, right? We would get infinity over infinity. We'd use L'Hopital's rule, we'd wind up getting 0, which would tell us nothing. The test would fail. Then you'd be thinking geometric. And you go, wait a minute, hold on, I do have an n in the exponent, don't I? But the problem is you have an n here as well. So if that n wasn't there, and that was like a 1, then that would be geometric, and that's what I would do. But because the n up top, it's not geometric. So then you think, is it harmonic? Well, no, it's not a constant over linear. So the only other thing you have is the integral test. So you're going to convert this over to f of x equals x over e to the x, right? You've got to show that that's continuous, right? You've got to show that that's positive, and you've got to show it's decreasing. And then once you're able to do that, then you're going to set up the integral, right, from 1 to infinity. And that integral, anyone have a guess as to what that integral is going to take? Don't tell me. I don't want to know. I don't want to know. But I want you to tell me by turning that into me.